apologies everyone for that extended delay. Hopefully next time we'll get into the room a little bit earlier so that we can get set up in time. Before we get going on the main business of today, just a couple of announcements. One is that I remind you that there's no seminar next week, but we will be reconvening in 6th week for 3 more seminars for the end of term. And also, I've heard from several of you that you want to come to dinner. There's space to squeeze at least one more in. So anyone who wanted to come to dinner but hasn't said, please come and tell me. So, on to the main business. It's a real pleasure to welcome Simon. A few years ago, I would have said, as is often said, Simon needs no introduction, and of course by reputation he doesn't, but for some of you he won't be quite as familiar as he was to us all a year or two ago. So Simon was perhaps not a pioneer, but an early adopter of the physics and philosophy degree at Oxford, then did a PhD at Chelsea College with Michael Redhead, came back to Oxford as a postdoc, was at Harvard, and then came back to Oxford as lecturer in philosophy of science. I think when I came back as a graduate student in 1996, from there transformed into professor in philosophy of physics, became a tutorial fellow at Merton, and has been a pioneer of several areas in philosophy of physics that have been very influential. The godfather, perhaps, of the decoherence-based renaissance in the Everett interpretation, but also well known for work in symmetries, other work on probability in quantum mechanics, on identical particles in quantum mechanics and symmetries. So, Simon, it's lovely that you're still with us, still giving talks. Over to you.
Thank you, Ali. I do appreciate that, and thank you all for being here and putting up with us today. IT. So I'm going to say something right at the beginning, which is that nothing that I will say will disturb in any way the decoherence-based Everett interpretation, including the work that's been done on probability, most notably by David Wallace. Okay, so having said that, okay, let's put it this way. David's approach is functionalist, broadly. If you take philosophy of mind and you've got a functionalist approach to the philosophy of mind, you will probably deny and reject any attempt to give some other analysis of what is mentality, which is not functionalist. So if you have that sort of view of what functionalism is, then what I'm doing will be contrary to a functionalist approach to probability. But another way of thinking about functionalism, or behaviorism indeed, is it gives us access to the mind. It enables us to study and pursue questions relating to mentality. And that is not to reject the possibility of some other analysis of what is mentality. So I just hope that sort of situates me a little bit vis-a-vis what has now become orthodoxy. Okay, so I'm starting off, and here's the great man. So this talk is begin with him and end with him. But let me just dive right in to operate my. How do I change windows? I see. So postulates for physical probability. So I ask you to read those postulates. The first 3. Well, the second is not altogether uncontroversial. One could have a view that physical probability, whatever it is not synchronic. But it's fairly widespread, and there are traditions going back in history of physics that treats, for example, thermodynamic probability as synchronic. In quantum mechanics and so forth, it is synchronic. So, but these are defeasible. These postulates may be wrong. That's fine. I think 1 and 3 can't really be wrong and still have probability, although 3 might be relaxed a little bit. And I'll come back to that point, that one might, relax a little bit. So the main one is number 4, which I'm calling intrinsic. So the idea is that the probability, and this is physical probability, not epistemic, physical probability can only be changed, probability of X, if there is a change in X. And the idea is that these elements, X, Y, Z, and so forth, range over really the ontology. And the physical state itself may be part of the ontology. These axioms are supposed to be extremely general. But they do clearly, I put to you, they do clearly rule out epistemic probability. So if you look at this number 4, this intrinsic business, I mean, you've got 2 envelopes and you put a lottery ticket in one of them and you scramble up the envelopes and you separate them out and you send them to far places. Alice and Bob, and you look at Alice and her environment and her envelope and everything, and nothing physically changes when Bob opens his envelope. But of course, when Bob opens his envelope, if he finds the lottery ticket, Alice's probability goes to 0. If he doesn't, Alice's probability goes to 1. The probability has been changed at a distance. Okay, so I think that is sort of fairly straightforwardly contrary to number 4. So I want to rule out epistemic probability. I'm looking for a criterion that distinguishes epistemic.
Right, Simon, before we move on, in 4, is the statement quite right? So do you mean mu of x can only be changed if there is a change in that which has the property x?
No, in x. X is part of the ontology. So I very much welcome clarification on points, but at the same time, I think let's see how the thing progresses, and perhaps then you can come back if you find this to be concerning. Okay, so now the Bell context, of course, EPR à la Bohm. So here's Alice and Bob. This is the source of spin systems typically. And here they've arrived, and here's a schematics diagram of the setup. And I hope it's familiar to you all. The idea is that Alice and Bob can each choose from one of 2 spin components that they wish to measure. They can change the settings on their apparatus. They can do so freely. They perform the measurement many times. And then somehow the results are all collected together. Charlie is floating above and acquires all of the data and finds extraordinarily, correlations that are very difficult to explain on local causal grounds. Some notion like that. Okay. So here are the 3, the first 2 are familiar. These are the 2 conditions that are normally used in derivations of Bell inequalities. Bell didn't start with them. He started with factorizability. These 2 conditions were then worked out really in the 70s, so quite some while later, that the 2 together then give you factorizability. So parameter independence, what setting, when Bob changes his setting on his measurement apparatus, that it doesn't change the probability for Alice's outcome S. The little a, little b, these are subscripts indicating the spin components that are being measured. Conditional outcome independence says, again, Alice's probability of outcome S isn't changed when, when Bob gets outcome T. Okay, so these very familiar conditions, I hope they make some sense to you already. Lambda independence is a bit peculiar, but it's suggested by my postulates. I mean, why not? You can perhaps change lambda. Now, in a way, this is all taken into account in the usual framework, because lambda, whatever it is, the hidden variable or whatever the underlying entities are, is going to interact with the measurement apparatus and will thereby change. So, as it were, future directed changes in lambda is already taken into account in the normal way. But these postulates, they're synchronic. They say nothing about the past and the future. So there's possible questions about, well, can lambda be changed in some other way? Okay, so I'll come back to looking at these postulates. This is part of the principal theory, as applied to the EPR setup towards the end. But for the moment, I just want you to, I invite you really to think of this in terms of the parameter settings, the outcomes themselves, and probabilities for outcomes. All of these things can be fitted into this framework, this way of thinking in these postulates. I mean, indeed, one can think that the parameters are standing in for the entire instrumental setup, the apparatus itself. Maybe Alice and Bob, they rebuild their apparatus. They have control over it. Okay, now a further point to make is that I don't think there are any direct implications of these conditions without some condition of no action at a distance. Because the point about these postulates, and look at this fourth one again. Suppose you've got, think ordinary quantum mechanics, and you do the two envelope, or the one envelope in two boxes experiment. Sorry, there's two envelopes, there's one lottery ticket. You can frame that in terms of a quantum experiment, Einstein's photon box thought experiment. I think he developed in the 20s. So you have a photon in one box or the other. It's an entangled state in the two boxes. Alice and Bob are again very remote from one another. Bob opens his box. Now, in ordinary quantum mechanics, there would be an instantaneous, you'd get one outcome or the other, and Alice's probability again would change. And in ordinary quantum mechanics, the quantum state is not part of the ontology. Now, if the quantum state is part of the ontology and instantaneously changes at a distance, then you can satisfy these postulates. But you do it in a rather trivial way. Okay, so I'm showing you this to illustrate why really these postulates, they need supplementing with some principle like no action at a distance in order to really get leverage on the EPRB setup. So that's the thought.
This last equation, I'm a bit worried about it. I would have thought that lambda independence would be not, it's a statement as it's written of left outcome probability being independent of the little lambda.
Indeed. I agree.
I was expecting it to be a statement of the probability distribution of the lambda being independent of the setting choice little a, little b.
Well, let me come back to probability distributions over lambda, but I'm looking, whatever lambda is, lambda could be a deterministic hidden variable, for example. I'm looking at its action. Lambda could be the quantum state itself. I'm looking at its action. As far as these postulates go, maybe lambda can be changed. So
Well, it shouldn't.
it doesn't want to change in any other way. It is what it is.
And you don't want the dash on.
No, I don't want any change at all. Perfect as it is.
Okay.
All right, so let me move on. So I'm now translating these postulates into no-collapse quantum mechanics. And I don't need any more of the Everett interpretation than no-collapse. I just need unitarity, no-collapse. That's it. So the physical state is the quantum state. And this is to be something ontological, so it's really a part of the ontology itself. The Boolean algebra is indeed defined in terms of these components. It's a wholly arbitrary expansion, orthogonal states, of course, but otherwise wholly arbitrary. In this way, with these operations under Boolean algebra, I generate the entire, all of the elements of the algebra, and I can define union, set-theoretic union, intersection in the normal ways. I convert sums of vectors into a set of those vectors, and then I can go back again from any such set. I can go back to the sum. So in this way, we formally set up a Boolean algebra. And may I just make this point too? I'm only assuming a Boolean algebra this is not. If one were to extend to much more generally, then 1, 2, and 3 would really give you the premises of Gleason's theorem. But I don't have the premise of non-contextuality. This whole thing is framed in the context of a given Boolean algebra, a given expansion of the quantum state. So additivity, this from just taking over from number 3, and then intrinsic. This is the crucial one. So the claim is from 4, intrinsic, to this statement, that if a change does not change phi, then the probability of phi, under that change, the physical state has changed, but under that change, the probability of phi cannot change. This is the claim, intrinsic. And now the virtue of this, having this translation, is this theorem. And the theorem just says that in such an expansion, then the states, if of the same norm, Hilbert space norm, I often speak of amplitude, meaning real amplitude as opposed to phase. So if of the same norm or amplitude, then their probabilities must be the same. And so any notion of probability that satisfies these postulates, that assigns probabilities to components of the state when expanded, must agree then with this claim that if of equal amplitude, then of equal probability. Okay, so just give a little indication of how the proof works. So I'm rewriting the state just to make it a bit more. Sorry, why is that not changing? I've changed it here.
It has changed. It's caught up.
It's caught up. I see.
It's now gone perhaps too far.
Gone too far. Okay, good. It'll come back again. Right, I see. A bit of a delay. I have to be aware of that. So I've rewritten the initial representation. I've just relabeled it. So the idea is that we start off with this state psi. Phi A and phi B are subject individually to a unitary transformation that leaves all of the other states unchanged. Phi A is changed into some new state, phi C. The red indicates which component of the state has changed. Because it's the only one that's changed, all of the other probabilities must stay unchanged. And because the sum of the probabilities must be the same, the probability of this guy must be the same as the probability of this guy, and therefore of this guy, and likewise working up this way. And now the point is, if the norms, if the amplitudes are the same, then ZB and ZA are pure phase factors. They can be absorbed into the unitaries. So the final state is identical to the initial state. And the sigma algebra of the final state is identical to the physics of the initial state. So because the probability depends only on these things, the probabilities cannot be changed, and the only way that is possible is if these two probabilities are the same. Initial and final must be the same, if the amplitudes are the same. Okay, so let's now look at the constructive theory of probability. That's as far as I need to go with the principal theory for the time being. The constructive theory, you might think, is beautifully built to make advantage of this theorem, but it was sort of the other way around. I had the constructive theory, and then I looked for a theorem and what sorts of principles would give that. So that was just the evolution of thought. So the basic idea is expand psi, again, in any basis whatsoever, as long as the components have equal norm. So there's no constraint. So those of you familiar with earlier work on which this is based, and particularly the last time I gave a talk here on this, a year and a half ago or so, I was there constraining such expansions to the decoherent spaces. There's no such constraint any longer, and it's rather important that there isn't. So now consider, I should just add, since equiamplitude, therefore equal probability from my double theorem. But we'll stay in the background for a moment. Just let's look at the constructive theory on its own terms. So suppose there's a projector P for which there's an equiamplitude expansion, all of the components are eigenstates of P. I call the components of an equiamplitude expansion, I call them microstates. So an expansion in microstates with all microstates eigenstates. So if there's m of them that are eigenvalue 1, n minus m eigenvalue 0, as I've indicated, then the probability of P in the state psi is m over n. Now, I hope that is intelligible to you. If you don't find it intelligible, then
We've got problems.
But I hope it is intelligible. I mean, I think it's fine to be only cautiously intelligible, intelligible until we see what sorts of traps have been set or something like that. But I hope that is intelligible. If this is intelligible, then I think I'm done, actually, to be honest with you. Anyway, so, and indeed, if you calculate the Born rule quantity for that projector, then it's exactly what you think. And further, if you had some other equiamplitude expansion, all of whose microstates are eigenstates of P, and there's some other, there's M primed and N primed and so on and so forth, because the left-hand side is unchanged, the right-hand side must be 2. So M primed over N primed will equal M over N. So you've got a sort of uniqueness insofar as the condition is satisfied. Okay, so that's very simple. I would have hoped really not problematic, although one needs to know a lot more about what probabilities thus in this way construed can do, and where they arise and how they connect. I mean, there's 100 questions that arise, but we go one step at a time. And the next step is, well, what on earth are you going to do when you don't have such equiamplitude expansions, all of whose microstates are eigenstates of P? So this needs a further idea, which I called interval probability, but I since learned it's better called imprecise probability. There's a whole community that works on this stuff that I didn't know about. Mostly they do so in connection with epistemic probability. So there's a whole sort of development there that I've yet to properly engage with, although I need persuading that epistemic probability has to engage with interval probabilities as I'm using them. Anyway, I'll just call them I probabilities for now to be neutral. So this is the point that, well, quite generally, you always, any equiamplitude expansion will be in that form. Of course, it may be that there's exactly none that are eigenstates at all, in which case you've all of them Schrödinger cat states for the projection operator. Okay, so a non-eigenstate of the projection operator, I'm calling it a Schrödinger cat state. But there may be some that are eigenvalue 1, some eigenvalue 0, and some number in between that are these borderlines, these Schrödinger cat. And the point about these is that at least we can define upper and lower bounds on the probability. If for sure a third of the sample has some property P, and for sure another third does not have that property P, then whatever the probability of P is, it's bounded. Greater than a third, and it's less than 2/3. So it is of this form. And then it's a very simple theorem. All of the theorems I'm going to state are extremely simple. It's embarrassing, really. But anyway, so this theorem, the Born rule quantity lies in the interval. It's contained in the interval. It's definitely above or equal to the lower bound, definitely equal to the upper bound. Okay. So I now need more theorems. But again, they're very easy. So the first one, for a Hilbert space dimension greater than 2. It's interesting, isn't it? It's always the same thing with Hilbert space. Everything interesting kicks in as long as the dimension is greater than 2. So for any n less than or equal to the dimension of the Hilbert space, there exist infinitely many equiamplitude expansions. Okay, and if you just think in terms of 3 dimensions, it's very simple. You think of a vector, think of 3 vectors which are orthogonal to each other, that sum to give that vector, fine, you've got an equiamplitude expansion, now just rotate. You've got a continuum infinity of such. But this theorem is the one that really we need more so, that you can, in this case, where the dimension of the projectors and indeed the complement of the projection is infinite, then for any state psi and any n whatsoever, that's why you need the infinite the dimensionality of the subspace. If it's going to be for any n whatsoever, there exists an equiamplitude expansion into n microstates, all but one of which is an eigenstate of P. So if this, I mean, it would help if you had an intuitive feel for this, but I think it may just take a bit too much time if I try to do it. I think if you can think in terms of proof by induction, start off with a 3-dimensional subspace. Or, no, go from 2 to 3 indeed. It might be the easiest. But see that if you've got an equiamplitude expansions in an n-dimensional subspace, then you can create another n+1 dimensional expansion if the subspace has sufficient dimensionality, okay, with possibly one Schrödinger cat state. Okay, well, if you'll just take this as given or spend some time and prove it yourself, I haven't actually published a proof of this, but it's not hard. So then this follows immediately. Okay, so if I define I probabilities using this theorem, I can define my I probabilities for any n. I'm giving it a bold-faced mu there to indicate that it's these rather special expansions that are adapted to P. This is another way of framing this. Find an equiamplitude expansion adapted to P that diagonalizes P, all of whose microstates are eigenstates of P. All but one. I'm allowing the but one to still, I say, the equiamplitude expansion is adapted to P. So you can find these adapted expansions, all but one of them is an eigenstate. Whereupon it follows that the limit must be the Born rule quantity, because the Born rule quantity is contained within the interval, right? And the interval is of width 1 upon n. So you take n goes to infinity, the width goes to 0, you get identity with the Born rule. So you might think, gosh, well, good, you've got a proof of the Born rule. Well, I sort of didn't quite put it that way in previous work because I recognize that the difficulty with calling this a proof, I mean, if you go back and you think where this all comes from, we've got to be able to make sense of this, to make sense of this, and to make sense of that. So this, yeah, we've got to understand this as giving us a genuine probability, or bounds on a probability. Why should we consider these as bounds on a probability? What is it about these expansions? Well, it's an equiamplitude, equal norm. Okay, fine. But still, why should we count them as equally probable? Which is why I think I really need to go back to the postulates that I started off with. And with them in hand, I have then a proof of this statement where these things indeed have the meaning of probability, and therefore so do these, where equal in norm, therefore of equal probability. Which then gives me the proof that here what is going on is this is a constraint, upper and lower bounds. It is quite a long delay. Well, thank you. So that this is indeed an upper and a lower bound on probability, because it's whatever satisfies these postulates. And armed with that, I claim that this thing now is a proof. I think this is not the best way to... finally it comes. Okay. And indeed, I better keep pressing so I won't have to wait so long. And indeed, that thereby the postulates justified the constructive theory. And what remains, and I haven't given any indication of how this works, is to show that from the constructive theory you prove not the postulates themselves in full generality, of course not, but you prove the postulates translated into no-collapse quantum mechanics. So there's a sort of reinforcement or mutual containment. And it was sort of seeing this and being rather struck by it that I thought, well, this reminds me at least, I mean, I don't know if it works for you, but it reminds me of the relationship between Einstein's principal theory of SR and a constructive theory of Roth's clocks on Minkowski space-time. I mean, my constructive theory, I haven't, as it were, given, and when I come on to the Bell, EPR Bell apparatus, I'm not going to give a detailed analysis of the apparatus, of course not. It's going to be schematic. And similarly, in Minkowski space-time and a constructive theory of rods and clocks, we don't actually go into all of the minutiae of the way the rods and blocks are constructed. It's enough, Harvey has made this point many a time, it's enough that the relevant physics is Lorentz covariant. And I think, similarly, I would say it's enough for my constructive theory that there's no collapse and it's on Hilbert space. So, so I think there are parallels, but it may well be the case that they're rather superficial. And you know, if you judge it so, I'm happy to give up this way of framing the relationship between the two. But I found it helpful myself. So let's see. Let's go now to the EPR Bell setup. So the obvious thing to do, my constructive theory does not yet have any claim about no action at a distance. I need to put that in. And one could put the whole thing into a Lorentz covariant quantum field theoretic framework and try to analyze it that way. And I've even been mad enough to try to do that myself in an earlier life. And there have been some who have equally been brave enough, I won't say mad enough, to try to provide such an analysis. But the obvious way to do it is to introduce a tensor product structure which represents Alice and Bob and their apparatus and their spin systems and so forth, and restrict Alice and Bob's actions to local unitaries as indicated. Okay, so let me call that theory lambda many. It'll be obvious to you why I'm calling it that quite soon. So if we look at these probabilities that we're interested in, Alice's probability for getting spin outcome S, either spin up or spin down, one of the two, with her setting at A and Bob's setting at B, then is going to be, consider the equi-amplitude expansion adapted to the projector onto her spin up outcome, if that's what it is. So you'll decompose the quantum state in this way, and you will then, if it's adapted to that projector, you will then have a count of microstates, which will give you its probability, and that obviously has nothing whatsoever to do with whatever Alice is doing. We have identity here. So whatever Alice does isn't going to make any difference whatsoever. So parameter independence, it would seem, is just obviously satisfied. Okay, now conditional outcome independence is not satisfied. And that goes along with the fact that lambda many, of course, implies the Born rule, and the Born rule violates conditional outcome independence, as we all know, and satisfies parameter independence. But look, I do want to just question this a little bit, because so much hangs on it. I mean, if Everett's going to be local, this had better be right, or something like it. I think if lambda many turns out to be non-local, I would be very doubtful one could defend locality. So one thing that happens with parameter independence in arrival theory is pilot wave theory. So what happens there, because you've got the Born rule for pilot wave theory, it also satisfies parameter independence. Fine. But if you look at the individual experiment, this is parameter independence at the level of the probabilities. But if you look at the individual experiment, it violates parameter independence. Let me just indicate, sorry, I should have had those couple of things in there. Let me put in what happens when you have a deterministic hidden variable theory. So, if deterministic, the idea is the lambda deterministically determines the outcomes, S, and so forth. So these probabilities are all trivial, zeros or ones. You have some probability distribution over the source of the hidden variables. And it's this thing which then tells you the probabilities that you measure on repeated trials, supposing that you control the source, that whatever you're doing at the source, you're controlling rho. So you can reproduce rho. When you do the repeated trial, you've got the same rho. So what's happening with lambda many is at the level of the probabilities, this is not lambda many is not a deterministic hidden variable theory, so we take lambda as just being the quantum state psi. So these are just These are not deterministic things, these are probabilities. But could it be like pilot wave theory, that at the level of the probabilities, parameter independence is satisfied, but at the level of the individual experiment, the individual hidden variable, it is actually violated. There is action at a distance going on. And the parallel would be that if the individual microstates are somehow involved in some non-locality, some action at a distance. So could those individual microstates? And the point here is the microstates acting deterministically. They're going to be a product state for the two projectors of Alice and Bob. So conditional outcome independence will be satisfied. So if the microstates are satisfying conditional outcome independence and they're satisfying parameter independence, then you might think you've got a problem, because then you're going to get Bell inequalities forced. So there's some question, really, as to whether lambda many is perhaps concealing an underlying action at a distance in terms of the microstates, but at the level of probabilities, it's not apparent.
Okay. Can I ask a question just for clarification? Yes. I mean, it links to Jeremy's question. I mean, in that equation with the integral rho of lambda, I mean, generally one starts with a rho of lambda, which might also depend on the measurement settings, and the measurement independence postulate says no, they don't.
Rho will not
so
depend on settings.
You've built that in, but does that come from an earlier? Does that come from your earlier?
This is not yet. This row of lambda is coming in particular when you have deterministic hidden variable theory.
Right, but the fact you've just written it, you haven't written it.
I'm going to show this, so we'll see in a moment. Let me give a picture of the relationship as I see it between what I'm now going to call lambda 1. So take one of the microstates and imagine that with each experiment, one of those microstates is produced at the source and determines the outcomes, just as in pilot wave theory. And the question is this thing acting in some action at a distance? So a simple picture, you've got all of these balls in an urn, ball in an urn with replacement. I've actually got a picture that sort of doesn't include the replacement, and I'm sorry about that. I'm just trying to indicate graphically. So you take a ball out, you note whether it's red or green, red or blue. This is spin up, spin down. You repeat the experiment. This is all with fixed instrument settings. So the urn and the balls in it, they're all for those fixed instrument settings. And you return, but you build up a record of all of your outcomes. Now, if you do this a large number of times, the statistics of the outcomes that you've observed will probably match the statistics of all of the balls in the urn. Okay, only probably. And this is the law of large numbers, and the probability that comes in here will be whatever is the probability that determines the randomness with which you pick the. And in fact, this rho lambda, understanding lambda 1 as one of these microstates, all of the microstates are equal probability. So rho lambda is just flat in this case. And it's the same regardless of the parameter settings. Does that answer your question? Well, okay. So, the lambda 1 picture is rather like pilot wave theory, and the lambda many picture is you're not taking these balls out one by one. You're not looking at macrostates one by one. The whole lot is, as it were, taken out with each experiment. It's then divided into those that are blue and those that are red. This is measurement apparatus and the unitary evolution of dynamics that's appropriate for that, and all carefully engineered in order to do that, of course. And you end up with spin up with a whole bunch of red balls and spin down with a whole bunch of blue balls, but then the relative numbers again gives you the probabilities of that spin up and that spin down. So that's how lambda many works at the level of a single experiment. And it's sort of dual to lambda 1 working over many repetitions of an experiment. I hope you can see that sort of.
Simon, I haven't understood the definition of what lambda 1 is.
Lambda 1 is taking one of the microstates, defined in lambda many for a given parameter settings, A, B. You're looking for equi-amplitude expansion for those projectors. You're taking one of those microstates randomly.
But is the total ontology the ordinary quantum state psi plus the microstate?
No, this either replaces the quantum state. This is a wholly different hidden variable theory, one world.
Oh, okay. So
This could have been done in the 60s or 70s. Sorry. But the thing is, it violates it violates Bell inequalities. It gives you back the same probabilities as lambda many. It's the probability distribution which is uniform over the lambda ones. It's the correct probability distribution by the lights of lambda many. And indeed will give you the Born rule. So here's lambda 1, agrees with the Born rule, therefore violates Bell inequalities. So something's going wrong, right? It's got to violate one of parameter independence or outcome independence, right? That's the logic. Okay, oh, I should have said, I'm sorry, I missed out a little thing. There's my Schrödinger cat, okay? I got one of them in there. See, is it blue or is it red? Well, you know how to say. So you can deal with that. And of course, you make the number of balls here as large as you like. You know, it can be cosmologically large. There's no bound. So you can forget about the Schrödinger cat ball, is my point. So now the funny thing though is about this lambda 1, I've got a product state that is an eigenstate of these two guys. And that's a very funny thing. I mean, I can't really plug it into parameter independence is the point. With parameter independence, you're fixing the context. This is B primed, and this is B. But you've got the same lambda in the two cases. And if the lambda 1, if it's this product state of this form, well, it's just the wrong, you can't have that in both of those contexts. So this is a funny, peculiar theory, and I'm suggesting that there's something we need to think about, and it hasn't been really in the literature, certainly not in the period when Bell's time, something like this, whereby the lambda, the hidden variable in the context beta primed, is going to have to be different from what lambda is in the context B. Okay, so that's the idea. Okay. Now, let me just sort of set up the three theories that we're looking at: lambda many, lambda 1, and pilot wave. And of course, lambda many and pilot wave have really nothing to do with this. This is a funny thing, this lambda independence, because it's not the normal causal going forward interaction with lambda that is happening. The lambda primed is not changing just by Bob's normal causal processes. That is already taken account of up here. It's changing in some other way, and it has to be different because Bob has set his instrument settings to be primed rather than B. So somehow lambda primed has to change. So pilot wave has nothing to do with this. Lambda many has nothing to do with this. But lambda 1, it seems, does have to have something to do with this. And if you look at what's going on, it's sort of obvious what's happening. Such delays. Oof. So here's an expansion, equi-amplitude expansion appropriate to A and B settings. And it's just a string with repetitions. And there could be millions of these guys. Okay, the repetitions, what I'm ignoring are other degrees of freedom, such as mass degrees of freedom, for example, where each of these will have a different state tagged onto it, which would achieve orthogonality. Okay, but we're not bothering about that. So here's the expansion for AB. Here's an expansion for AB primed, same number in each. And the idea, essentially, is this, that the lambda here and the lambda prime need to be paired such that if I've got a lambda for AB, I can then say what would be the lambda if B were changed to B primed and answer, it would be one of these guys. And there would have to be a one-to-one correspondence between every such state in here and every such state in here. Really, just a straightforward one-to-one correspondence would be sufficient then to carry the counterfactual. And that is easily shown to be the case. So what you end up with is indeed lambda 1 satisfies this condition, and this condition really replaces parameter independence. Parameter independence isn't so much violated as it's just inappropriate, inapplicable to lambda 1. Okay, so I hope everyone's following. So now we've got an interesting situation. It's a one-world hidden variable theory, which is entirely free of action at a distance and violates Bell's inequalities. But of course, it does so by this funny business. And that, I think, really can only be understood in terms of retrocausation or possibly superdeterminism. You know, either Bob can't change his instrument setting, or rather he thinks he's changing them, making a free choice. Oh, I'll choose that direction. But actually, he was determined to do that by the hidden variable. Right? That would be superdeterminism or the retrocausal thing.
I think this is a short question, but explain me if needed. To make this thing with the question mark vindicated, am I right that the dimensionality of the projector B dash needs to be the same as the dimensionality of the projector B?
No. Not at all. These are all infinite dimensional. Well, I should say something more about this infinite dimensional projectors. It may sound shocking to people. So, just to put it to you, a hydrogen atom, a projector, well, any system which has position, needs an infinite dimensional Hilbert space. Okay. Any square root L2 space over some interval of the real number line, no matter how tiny, that's an infinite dimensional Hilbert space. So any physical system with anything like localization properties, a center of mass, degrees of freedom, for example, will live in an infinite dimensional Hilbert space. You can look at just spin degrees of freedom, and of course that finite dimensional Hilbert space for that. But you just take that you're just ignoring the factor space, which would be an infinite dimensional Hilbert space. So if you should have a whiteboard really. So if you've got you've got something like, I mean, we typically just work. Gosh, I don't have much time.
Simon, you
agree with your conclusion.
Okay. So, what am I trying to show? So you might just work with projectors on finite dimensional Hilbert space, but really what you're doing is you're working with these guys, and this is always going to be infinite dimensional. Okay, sorry, that's just an aside. I see I'm going to be running out of time, so I must get on.
So we started at 12 minutes past.
But that's something. Okay. Okay, so let's just unreservedly now look at lambda many. Forget about pilot wave and lambda 1 and so forth. It was really the point of lambda 1 was to confirm that there's nothing funny going on with the parameter independence. It really is not like pilot wave theory. The probabilities are not disguising some action at a distance going on at the level of individual microstates or in the superposition. We do violate conditional outcome independence, and completeness is a related condition. I mean, from the definition of a conditional and this, then you get completeness. And vice versa, from completeness and the definition of a conditional, you go back to it. So what is going on with this violation? Typically, this is understood to involve action at a distance. Okay, now it's quite easy to see, though, and this is well known, I'm saying very little that's new. I'm just situating it in a different way, perhaps. Conditional outcome independence, if you've got a product state and you're looking for an equiamplitude expansion adapted to this product of these projectors, well, you'll just expand phi equiamplitude over this projector. You'll expand xi over this one. Anyway, and you'll just take the product of the two. You know, you'll just have one big NA of these guys, NB of these guys, product them together. You're just going to get NA times NB terms in total, and of them, MA times MB divided will be those that give outcomes S and T. and so forth. I mean, really, it's trivial and obvious. And therefore, of course, it's sort of trivial and obvious when this will be violated, namely when you do not have a product state. So that's just the well-known claim that completeness is satisfied if you have a product state. And when it's violated, that is the signature of entanglement. Fine. And there's just one further question to pose at the level of lambda many, which is, well, how do I express the idea that there's no action at a distance when Bob does his experiment? Because that was what these conditions were intended to capture. And it seems that, well, the right thing to require is that when Bob performs his measurement and there's a superposition of outcomes produced, that makes no difference to Alice's probabilities. Which is obviously true. Just look at any local unitary that produces Bob's measurements process. And of course, that will make no difference whatsoever to Alice's probabilities. So I do claim on this basis, and the talk could in a way come to a stop now, that lambda many is perfectly free of action at a distance, not a hint of it. But I'm going to go on, because in a way, this is disappointing. In a way, it shows that, if this is right, all of this fuss about Bell and violation of Bell inequalities, what does it really amount to? It was all a mistake. All that it really is a test for entanglement, and it doesn't have the implications that it was thought to have. Well, certainly I can't do much more within lambda many. I mean, within lambda many, all I can say is, well, does it or does it involve action at a distance? Answer, no. So to say something more interesting, what is the interest of Bell's inequalities after all? It's if the arguments that lead to the inequalities are very general, because then from the fact that the inequalities are violated, we learn something important. So it's more interesting, really, to approach the question from the point of view of my principal theory, not lambda many, but supplemented with, well, I'm calling it Locke. I'm a student of Michael Redhead. What can I do? You know? It's beaten into me somehow. But what I mean by that is no action at a distance. So the claim is, and one needs to reflect on the postulates, and in particular the postulate 4. Do they have these consequences now supplemented with no action at a distance? And my claim is that they fairly transparently do, except for outcome independence. Parameter independence, I think, very straightforwardly and transparently follows as a consequence of the principal theory and Locke, no action at a distance. But the conditional outcome independence, it depends whether or not there's something like joint outcomes arising is on the table. If it isn't, if there's only a unique outcome produced by Bob's experiment, then I think the point here is that it would be a change. Bob's experiment would result in a change, which, what are we doing here? We're embedding principal theory into a sort of a very, almost a common sense physics. There would be a change in Bob's vicinity that would have to be counted as such in that common sense physics. And by 4, that change should not make any difference to Alice's probability. So in that situation, it seems to me that you do force conditional outcome independence. I should have said, look, we had the retrocausal business. Let's get rid of the retrocausal business. Just put it to one side. It's interesting. It comes up, this physical state independence. It's suggested by the postulates as something to look at. We have looked at it. We see that it works, but it involves retrocausation, and I'm now going to ignore it. Okay, but I think it's to the credit of these postulates that it, as it were, signals the fact that, well, look, what about some condition of this form? And if lambda were not in the ontology, Well, then this would follow. You'd have to have, if lambda had nothing to do with the ontology, then 4 will straightforwardly say a condition of this form, because nothing has changed in the ontology. But lambda does, of course, have something to do with the ontology, and this common sense physics that we're using assumes so. It assumes that Alice and Bob, their spin systems, is part of the ontology, interacts with their apparatus, and whatever the physical state is over and above those two spin systems is also part of the ontology, but how it bears is in terms of expressed in terms of these conditions. But if Bob, though in performing his experiment, produces the superposition of outcomes, then I think it's not at all obvious that this should be the appropriate condition. This seems to be the appropriate condition. Now, can I just push back on this briefly? I've only got 5 minutes, but I am near the end. You might think, even though Bob produces a superposition, that consists of two things that are going on in his laboratory. Each of those things is a physical change. So why should not this kick in for each of those changes considered individually? What forces us to look only at the total change, as it were? I think this would be quite a powerful objection, and it may even prevail, although I think not. And the reason I think not is because if you consider something going on in Bob's remote vicinity, opening and closing the laboratory door or something like that, fine, that should not make a difference to Alice's outcome. He switches on the apparatus, that shouldn't make a difference, fine. Lots and lots of things can go on in Bob's vicinities that should not make a difference. But what if Bob performs a miracle? He performs his experiment and produces a single outcome. This would be a miracle in no-collapse quantum mechanics. Do we require this to kick in when Bob does something miraculous? When the process in question or the change in question is contrary to physical law? I just put it to you that is asking for far more than no action at a distance. It's asking for something much more than that. So that is my defense as to why really only joint outcome independence is required and is easily satisfied once it is on the table. If it's not even on the table, you won't even think of it, and it won't occur to you. So this, I suggest, is the sort of logical, just to put it in symbolic terms. The principal theory implies this conditional. Now, this conditional is well known to everybody here, I hope. And many people will say that this conditional stands on its own. You don't need PP at all. And there have been arguments to that effect. Maybe that's true. It's possible. Maybe you can make the case without PP, but I think PP adds clarity. That's my claim. And I don't think, can anyone name a paper that successfully leads to that conclusion? Can anyone? Paolo, you've worked on the paper recently, haven't you, by Vagel and McQueen? You don't think it does. So oddly, Tim Maudlin almost seemed to agree in his 2014 paper. I say oddly because I don't think he really means it. He doesn't want to say that because, of course, it's logically equivalent to this. And given that Bell does not hold, given that locale no action to distance is one of the most best tested principles in all of physics, and if we want to reject therefore causation, then the overwhelming implication would seem to be to non-uniqueness. But having said that, let's be aware of the Einstein photon box paradox, and let's just go back to it. So here's the box. See, there's a photon put in superposition in the two boxes and actually gets entangled with the two boxes. So Alice and Bob, they shoot off again, they do their thing, and they arrive, and they've each got a box. Okay. So now, again, if Bob, when he opens his box, produces a unique outcome, then the same reasoning kicks in. If there's no action at a distance between Bob and Alice, then Alice's probability should not change for finding the photon in the box, but if there's a unique outcome, then it must. So, in this case, I say, locality and uniqueness implies not PP. My principal theory goes down the drain. Okay, that's fine. But then what does Bob do? Well, he opens the box. And this is a cat who is in a state of neither being dead or alive. So, of course, we could indeed consider the logically equivalent sentence. That if the postulates are true, this principal theory, then locality implies non-uniqueness all on its own. Now, I agree there's something unsatisfying about that. I mean, and part of the reason why it's unsatisfying is because the obvious thing to say about the Einstein photon box case is, well, the theory is incomplete, and the photon's actually in one box or the other, and that's all that's going on. There's no action at a distance, right? And I think that's correct in that that's to be happy with effectively, it's to be happy to contradict this axiom if we're talking about epistemic probability, ignorance, something of which we're ignorant. Of course, that's precisely what Einstein thought the photon box experiment indicated, that the only way that this could make sense is if actually the probability is bound up with ignorance and the quantum mechanical description is incomplete. But if you think, no, there's really something called physical probability, think of it like a propensity. Harvey reminded me of a very nice, lovely account in Don Giller's book on probability with propensities. So you really think something physical, it's something local, it's something there. Then for it to be changed at a distance by Bob opening his box is spooky action at a distance. The same spookiness that there was in Bell. The difference is that, as I say, the photon in the box thing, the argument for incompleteness, well, it seems that there's no problem, the photon's in one or the other, what's the difficulty? Forget about this foolish axiom, let's make do with epistemic probability. And you can't do that in the Bell case. So that's why the Bell case is, in a way, much more interesting or important and so forth. But in terms of the logic involved, it's somewhat similar. Okay, so I'm coming back to Bell, just as last comment from Bell, which was quoted as well by Chris on Harvard's paper on changing 2020 paper, I think. So this is in his 6 possible worlds. The many worlds interpretation seems to me an extravagant and above all an extravagantly vague hypothesis. I could almost dismiss it as silly. And yet it may have something distinctive to say in connection with the PR puzzle. And it would be worthwhile, I think, to formulate some precise version of it to see if this is really so. And then there's a comment here about existence, more comfortable, and so on and so forth. Anyway, so I think, Bell was not so closed to investigation. I think it shows he had an open mind. But I cannot but think this is the solution to his puzzles that he would have least liked, as he said of Bell. Anyway, so thank you all.
7 people in the queue, and I went from left to right, so I'm going to switch left to right to even things up.